When a system of equations has an infinite number of solutions, we can write what is called a general form for the solution. There is a general form for the solution to the example above. Since all of the points that are on the line that represents both equations are points where the y value is equal to 1/2 times the x value minus 1, that means the general solution is x comma 1/2 times x minus 1. This formula can be used to generate specific solutions. So, for instance, if we let x be 0, then 1/2 times 0 minus 1 is -1, so one specific solution is 0 comma -1. Another is, if we let x equal 2, for instance, then 1/2 times 2 is 1, minus 1 is 0, so 2 comma 0 is another solution, or a point on that line. The general solution gives us a way to generate those specific solutions. Now we're going to move on to linear inequalities. Those are inequalities that have two variables, and the solution can be graphed in the x comma y in the xy plane. So if I use a table of values, and if we're graphing the inequality y is less than 1/2 x plus 3, I'm going to use multiples of 2 to substitute for x, since we're multiplying that by 1/2. So I'll use -2, 0, 2, and 4. 1/2 times -2 is -1, plus 3 is 2. So when x is equal to -2, let's remember what that looks like. That's a vertical line, so I'm going to draw that very lightly. Then I'm going to shade over top of that y is less than 2, which is an open circle on y equals 2, and shading downward for values of y that are less than that. When x is 0, y is less than 1/2 times 0 plus 3, which translates to y is less than 3. Remember that x equals 0 is a collection of points on a vertical line, and we are graphing points that have a y value less than 3. So that would be an open circle on 3 and shading downward. For our next point, x is equal to 2, 1/2 times 2 is 1, plus 3 is 4. So for x equals 2, y is less than 4. The points where x equals 2 are a collection of points on a vertical line, and when we graph the points on that line that have a y less than 4, that would be an open circle on y equals 4 and shading downward. For a next value, we can use 4. 1/2 times 4 is 2, plus 3 is 5, so y is less than 5. When x is equal to 4, that represents all points on the vertical line x equals 4. And we're going to shade the y values that are less than 5, which means open circle on 5 and shade downward. Now you can see there's a trend here, right? We are shading downward from the line, and we are not including those points that have open circles on them. Now there are lots and lots of points in between the values that I chose for the table. So what I want for you to notice is that the line y equals 1/2 times x plus 3 actually graphs at each of those endpoints right there. Now we have to have a way to say that all the points on the line are not included. Instead of writing open circles on those lines, what we are going to do is we're going to dash the line to indicate that the line is not included, and then we are going to simply shade all the points below, and you can kind of either shade it with your pencil and shade it in completely, or you can just put crosshatches on that area. All right, so I want you to notice that the line y equals 1/2 x plus 3 divides the coordinate plane into 3 regions. Those that are on the above the line, which we didn't shade, those that are below the line that we did shade, and those that are on the line, which we indicated with dashed line that those are not included. Rather than make a table of values to graph a linear inequality, we're going to use an easier method. We're going to first start by replacing the inequality greater than or less than with an equal sign, and then solve the equation for y if possible, and then graph the dashed line if the original inequality was greater than or less than, and graph a solid line if the original equation or inequality was greater than or equal to or less than or equal to. And then we can use test points to determine which side of the line to shade. So, for instance, I'm going to take this inequality, 2x minus 3y is greater than or equal to 12, and I'm going to change it to equal so that we can graph the line. So negative 3y is equal to negative 2x plus 12. Let's divide through by negative 3. And that gives us y is equal to positive 2/3 x minus 4. Since the original inequality had an or equal to, I'm going to graph that as a solid line. So here's our y-intercept, and then using our slope, we can graph a couple more points, and we'll graph with a solid line since we had or equal to, which means that the line is included, or equals is included. The next thing that we need to do is determine which side of the line to shade. So we're going to test points in the original inequality. I'm going to test a point that is above the line, and a point above the line is 0, 0. And I'm going to take the original inequality and I'm going to replace x with 0 and y with 0. And see if that is greater than or equal to 12. 2 times 0 is 0. 3 times 0 is 0. And 0 is not greater than or equal to 12, so that is false. That means we will not shade above the line. Now let's test one that's below the line. And a point that's below the line could be, for instance, anything in that area below. So I'm just going to pick a random point here. Let's say 5, negative 3. Test that point. And 2 times 5 is 10. Negative 3 times negative 3 is positive 9. 10 plus 9 is indeed greater than 12. And so that's a true statement. That means that I will shade below the line. So I'm going to take my highlighter here and shade this area below the line. We indicated a solid line to indicate that the points on the line are solutions as well, in addition to the shaded points below the line. There is another way to solve this particular exercise, or to graph this solution set, and that other way involves a different strategy. To graph the solution set this way, we can just simply take the inequality and solve for y. And when we divide through by negative 3, that's going to switch the inequality's direction. And because we have y is less than, think about where you find y values that are smaller. They are below. We're going to use a solid line, and then we're going to shade below. In general, I'm going to favor this second way, but you can always use that first way. We have a second inequality in B to shade. That's x is less than 5. First, we're going to graph the borderline, which is x equals 5, but it's going to be dashed since there is no or equal to. And so I will make a vertical line on x equals 5, and I'm dashing it to indicate that the line is not included. And since x is less than 5, when we graph values that are less than 5, we find those on the left. And so I'm going to shade the area to the left of that line, and the dashed line indicates that the points on the line are not included in that solution set. In example 5, we are looking to see if each point is a solution to the inequality that's graphed. And we see each inequality's graph in Roman numerals 1, 2, and 3. So to test the point -1, -1, I'm going to look and see if it's part of the shaded region. And for Roman numeral 1, it is part of the shaded region, so it is a solution. So I'm just going to write the word yes here for yes, this is a solution. For number 2, -1, -1 falls in an unshaded portion of the graph. So that no, that is not a solution. And for number 3, it falls in an unshaded portion, so no, that is not a solution either. Now let's take a look at the point 6, 0. 6, 0 is something that we can't actually graph in this grid, but if we did have the point 6, 0, it would be somewhere over here to the right on the first graph. That's in an unshaded portion, so no, that is not a solution. For Roman numeral 2, it would be to the right, and that would fall into a shaded portion, so yes, that would be a solution. And for Roman numeral 3, falls over here to the right. That's an unshaded portion, so no, that's not a solution. Now let's investigate another point, and that third point is the point 0, -2. For the first graph, 0, -2 is in a shaded portion, so yes, that's a solution. In the second graph, 0, -2 is in a shaded portion, so yes, that is a solution. And in Roman numeral 3, 0, -2 is right on the line, which is dashed. That indicates that it is not included, so no, it is not a solution. And now let's take a look at the last point, 2, 0. 2, 0 in Roman numeral 1 is right on the line, but the line is solid, so that is included. 2, 0 is in the shaded portion for number 2, so yes, that is a solution. And 2, 0 is outside of the shaded portion for Roman numeral 3, so no, that's not a solution. For example 6, we are going to graph each nonlinear inequality in the xy plane. So I'm going to graph my border by graphing y is equal to the absolute value of x plus 3 minus 2. Now remember, we can use the new origin approach for this. So the new origin approach would be to graph the point -3, -2. That's your new origin. And thinking about the absolute value function, if I move 1 to the right, I go up the absolute value of 1. If I move 2 to the right of the new origin, I go up the absolute value of 2. And then for moving left 1, I go up the absolute value of -1, which is +1. So again, we're going up. And then left 2 and up 2. That gives us that V shape right there. That border line will be dashed, or the border curve here, or graph, whatever you want to call it, will be dashed since we don't include that as part of the solution. And then we need to determine which side of the graph to shade. Since its y is greater than, that's going to indicate that we shade above. So I'm going to grade or shade on the top side of this line. So this portion of the xy plane is shaded. I know I said line before, but this graph is what I really meant. All right, so dashed graph and shade above. Let's take a look at example 6b. For example 6b, our border line is y is equal to -1/2 times x minus 2 cubed. Our new origin is the point 2, 0. And then if you wanted to use a modified table of values for this parent function, you certainly may. X cubed, and -1/2 x cubed once you take all of the addition subtraction out of it. So for the x values, we'll use -2, -1, 0, 1, and 2, cube them, and then take -1/2 times each of those values. And then graph those points relative to the new origin. So the first point, -2, 4, means 2 to the left and 4 up. The next point in the table, -1, 1/2, means move to the left of the new origin and up 1/2. 0, 0 means graph on the new origin. 1, -1/2 means move 1 to the right of it and 1/2 down. 2, -4 means 2 to the right of it and 4 down. There is an or equal to, so we're going to make a solid border. And then, since we have y is less than or equal to, we will shade below. So I'll shade below every point on this graph. And to some of you, that's going to look like the left side, but it's actually below every single point on this graph. For the next portion, we're going to graph a system of inequalities. And so we need to find the region that satisfies the first inequality and the second inequality, or find their intersection. So we can start by graphing each of the original inequalities. Our border line for the first inequality is x equals -2, which is a vertical line. Since we don't have an or equal to on it, I'll make it that a dashed line. And then y is equal to x plus 1 is our second border line. That has a y-intercept of 1 and a slope of 1. So I'm going to graph that line with a dashed line as well, since we don't have or equal to. And then I'm going to do two shadings. I'm going to shade, since x is greater than 2, I'm going to shade on the right side of that line. And then, since y is greater than x plus 1, I'm going to shade on the top side of that line. What we can see here is that there's a common area. And what we really want to indicate is that the solution lies in that common area, which is the area here that got shaded twice. That's the intersection of the two shadings. Now, you don't have to graph each individual one first. You can just graph and say, where is the region that is to the right of the first line and above the second line? and that's fine. For b, our borderline is y is less than negative 2x plus 1. We can solve it for y. So we have a y-intercept of 1 and a slope of negative 2. And remember, a slope of negative 2 makes this a falling line as you move from left to right. And the line is dashed since there is no or equal to. Now let's work with our second inequality. I'm going to solve for x by subtracting x from both sides. I'm solving for y by subtracting x from both sides, and now divide through by negative 1, which changes the direction of the inequality. So y is greater than x minus 3, and this line, y equals x minus 3, will get a solid line since or equal to is included in the inequality. And next, since the first inequality is less than, y is less than, we're going to shade below. The second inequality is y is greater than, we're going to shade above that line. So the points that lie below the first line and above the second one are going to be the points that lie over here in the coordinate plane. They are below that dashed line, but at the same time are above the solid line. In C, we have two nonlinear graphs. Y is less than or equal to negative absolute value of x plus 4. So this is an absolute value graph that has been translated up 4, and the negative indicates that the graph is vertically reflected. So we're going to get that V shape. This will be a solid graph since or equal to is included. And then our second graph has an origin point of negative 1 comma negative 2. And it's a quadratic function, which means we're going to go over 1 from the new origin and up 1, over 2 from the new origin and up 4. And then the same for the left. Left 1 and up 1, left 2 and up 4. And that gets a solid line or solid graph as well. And you'll notice that this is a little bit more complex. For y is less than or equal to, we'll shade below the V-shaped graph. And for y is less than or equal to, for the quadratic function, we'll shade below that graph. So I want the portion that is below both graphs, and that portion would be the portion right here below both graphs. Last example, we have 4 inequalities, but 2 of the inequalities are fairly simple single variable inequalities, and the other 2 are lines. The first inequality is a horizontal line as the borderline, y equals 3. It's a solid line since or equal to is indicated. And then the second line is x is less than or equal to 2. Solid line again, vertical, because x equals 2 is a vertical line. And then I'll take and add x to both sides for the third equation. That will give us y is less than or equal to x plus 5. That has a y-intercept of 5 and a slope of 1. and or equal to is indicated, so that border gets a solid line. And then the last equation, or rather last inequality, is y is greater than or equal to negative x minus 3. Once we subtract x from both sides, that has a y-intercept of negative 3 and a slope of negative 1. And that again has a solid line since or equal to is indicated. And now we need to determine where to shade. So y is less than 3. That's going to be shading below the horizontal line. And then x is less than or equal to 2. That's going to be shading to the left of the vertical line. And then for the next inequality, we'll shade below that line. And then for the next inequality, since y is greater than or equal to, we'll shade above. So shading below the horizontal line to the left of the vertical line, and then below y is less than, or y is equal to x plus 5, and above y is equal to negative x plus 3. That's going to give us this portion of the graph right here. So above one line, below the other, below the horizontal line, and to the left of the vertical line.